We are going to start now the lecture 2 of chapter 5 class 11th mathematics, complex numbers and quadratic equations. So in this lecture we start with some results on modulus and conjugates of complex numbers. So in our previous lecture we have already studied the definition of the modulus and the conjugate of a complex number. So the definition for the modulus, we are saying, when we are defining the modulus, we are saying mod of z, it is equal to square root of a square plus b square, where z we are saying it is a plus iota b, and the conjugate of z we are saying it is a minus iota b. This is the definition for both these things. So the first property we have over here, we are going to prove is that z bar is equal to z, that is the conjugate of z is equal to z. So to prove this result, we are saying suppose z is the number of the form a plus iota b, then z bar will be a minus iota b, and now if we calculate the conjugate of this number, we will again obtain it is a plus iota b, and this is equal to the value z. So we are saying z bar this is equal to z. Second thing we have to prove now it is that z bar, that is equal to mod of z square, and that is equal to real part of z square plus imaginary part of z square. So we have the value of z and we have the value of z bar. We have value of both these things. So if we multiply z with z bar, the answer we get it is a plus iota b into a minus iota b. So this is equal to a square plus b square, and this is equal to mod of z square. This is the first part. And when we are talking about a square, it means this is we are writing it is real part of z square plus imaginary part of z square. So this is the proof of the second part. Third, we are saying that z plus z bar, we have the value of z, we have the value of z bar. So if we are calculating z plus z bar, the answer we will have it is a plus iota b plus a minus iota b. So this is equal to 2 times a. So this is equal to 2 times real part of z. So from this we can also write that real part of z, that is equal to z plus z bar by 2. We can also write it in this form, that real part of z is z plus z bar by 2. The proof we have it is the imaginary part of z we are talking about. So if we are doing z minus z bar, we are writing it is a plus iota b minus a minus iota b. So this is equal to 2 iota b. So this is equal to 2 iota into imaginary part of z. So we are saying that if we have to calculate the value of imaginary part of z, so it is equal to z minus z bar by 2 iota. Next we have to prove is that if z is equal to z bar, we have to prove is if z is equal to z bar, then imaginary part of z is 0, that is the number is purely real. So when z is equal to z bar, so this thing implies us that a plus iota b is equal to a minus iota b. Now by the equality of the complex numbers, we know that this a is equal to a, and this b should be equal to minus b. So this implies us 2 times b is equal to 0, and this implies us b is equal to 0. So this thing means that imaginary part of z, that is equal to 0. It means the number is purely real. Next we are calculating the value of z plus z bar, and we are saying suppose this value is equal to 0. In this case basically we are saying z is equal to minus of z bar. So we are writing z plus z bar is equal to 0. So this thing implies us that a plus iota b plus a minus iota b, that is equal to 0. So this implies us a is equal to 0. This means real part of z is 0. So this thing means that the number is purely imaginary. So the condition for the number to be purely imaginary is z plus z bar is 0, and we are saying that if z is equal to z bar, then the number is purely real. Next we have to prove is that z, talking about this condition over here, plus z2, z1 plus z2 whole conjugate, that is equal to z1 conjugate plus z2 conjugate. So to prove this result, we start with this condition. So we are writing a1 plus iota b1 plus a2 plus iota b2. We are talking about the conjugate of this number. So this is basically equal to a1 plus a2 minus iota b1 plus b2. So we are saying this is equal to a1 minus iota b1 plus a2 minus iota b2. So this is equal to z1 bar plus z2 bar. So we are saying z1 plus z2 conjugate, that is equal to z1 conjugate plus z2 conjugate. This is what we have to prove. Next is we are saying z1 conjugate minus z2 conjugate. So this is similar proof is there. We are writing it is in this form. So on solving this value, it is conjugate over here. So we are separating the real part. It is a1 minus a2, this is the real part. b1 minus b2 is the imaginary part. After this we are taking the conjugate over here. So this plus sign is changed to negative sign, and we obtain the answer in the form z1 conjugate minus z2 conjugate. So proof is almost similar to the proof we have done in our previous case. So you can try this proof at your own. Similarly, for the next case, we have z1 z2 conjugate we are talking about. So if we write the value of z1 into z2, we know the value is a1 a2 minus b1 b2 plus iota a1 b2 plus b1 a2. So if we take the conjugate of this term, we are talking about the conjugate of this term. So this minus sign we get over here, this plus sign is replaced with minus sign, and this term again we can write it in this form, and this is equal to z1 conjugate into z2 conjugate. And similar result we have for z1 over z2. The condition we have is z2 is not equal to 0. So we are writing it is a1 plus iota b1 divided by a2 plus iota b2. To solve this, we are going to multiply it with a2 minus iota b2 divided by a2 minus iota b2. So when we solve this value, when we multiply these terms, we obtain the answer in this form. So when we take the conjugate over here, we are taking the conjugate over here, this plus sign is changed to negative sign. Next, we are calculating the value of z1 conjugate over z2 conjugate. So that is equal to a1 minus iota b1 over a2 minus iota b2. To solve this, we are going to multiply it with a2 plus iota b2 over a2 plus iota b2. So when you will multiply these terms, you will see that the final answer you are obtaining, it is the same answer we are obtaining in both these cases. So the result we are getting over here is that z1 over z2 conjugate, that is equal to z1 conjugate over z2 conjugate, and it is division over here. So this condition z2 is not equal to 0 is important. Next we have certain properties related to the modulus of the complex numbers. So the first property we are saying, we are proving over here, it is z into z bar. You can write it is a plus iota b into a minus iota b. So that is equal to a square plus b square, and that is equal to mod of z square. Second property we are saying is mod of z, if we are writing, it is a square plus b square, and this is equal to mod of z bar. Z we are writing it is a plus iota b, z bar we are writing it is a minus iota b, and this is equal to mod of minus z, we are writing minus a minus iota b. So in this case the answer will be minus a square plus minus b square under root. So that will be equal to square root of a square plus b square. in this case the answer we will have it is square root of a square plus minus b square. So we are obtaining the same answer in this case also. The next part we have to prove is, it is given that mod z is equal to 0. This is implies and implied by z is equal to 0. So if we are writing mod z is equal to 0, so this thing implies us that z square, mod of z square is equal to 0. This thing implies us that a square plus b square is equal to 0. A and b, these are the real numbers. We are talking about a and b, we are having z is equal to a plus iota b, where a and b, these are the real numbers. And for real numbers, if a square plus b square is 0, so this thing means a is equal to 0 and b is equal to 0. So this thing means z is equal to 0, because we are saying a is equal to 0, b is equal to 0. We substituted over here, we obtain z is equal to 0. And this is what we have to prove, that if mod of z is 0, this is implied and implied by z is equal to 0. Next thing we have to prove is that mod minus mod of z is less than equal to real part of z is less than equal to mod z. So if we are considering z is equal to a plus iota b, then mod z is equal to square root of a square plus b square, and we have minus square root of a square plus b square is always less than equal to a, is always less than equal to square root of a square plus b square. Now why we are writing this result? We are saying that a square is always less than equal to a square plus b square, where b is some real number. It is square over here, so it is always less than equal to this. So if we take square root on both sides, we obtain that mod of a is less than equal to square root of a square plus b square, and it implies us this inequality. So we are having the answer in this form, and this is the value of minus mod z is less than equal to real part of z is less than equal to mod of z. Similarly, for the value b, we are saying, we are writing again mod of z is equal to square root of a square plus b square, and we are writing the inequality in this form, that minus square root of a square plus b square, it is less than equal to b is less than equal to square root of a square plus b square, and this thing implies us, this is the value of minus mod z, b is imaginary part of z, and this value we are saying it is mod of z. Next we have to prove is, the next result we have to prove is that mod of, we are talking about mod of z1 z2, that is equal to mod of z1 into mod of z2. So if we are taking these two numbers, z1 is equal to a1 plus iota b1 and z2 is equal to a2 plus iota b2, and we multiply these numbers, we are writing z1 into z2, the answer we have it is a1 a2 minus b1 b2 plus iota a1 b2 plus b1 a2. So if we take the mod over here, we are talking about the mod of z1 z2, we are writing it is equal to square root of a1 a2 minus b1 b2 square plus a1 b2 plus b1 a2 square. Now if we open these whole squares, we obtain this is equal to square root of a1 square a2 square plus b1 square b2 square minus 2a1 a2 b1 b2 plus a1 square b2 square b1 square a2 square plus 2 times a1 a2 b1 b2. These two values gets cancelled, and we are left with this term. We are talking about these two values, these gets cancelled, and we are left with this term. These two values are cancelled. So on adjusting these terms, we are taking a1 square common, b1 square common, we obtain the answer in this particular form, and this is basically the value of mod of z1 into mod of z2, because both these numbers, these are positive. We can separate these numbers over here and we obtain that the answer we get, it is mod of z1 into mod of z2. So we have proved this result, that mod of z1 z2, that is equal to mod of z1 into mod of z2. Next we have to prove is that this result we are talking about, that mod of z1 by z2, that is equal to mod of z1 divided by mod of z2. So to prove this result, we are going to start with, we are writing z1 is a1 plus iota b1, and we are talking about the value upon z2, so it is 1 over z2. So we are writing it is into 1 over a2 plus iota b2 into a2 minus iota b2 divided by a2 minus iota b2. So if we multiply these terms, we obtain the answer in the form, this thing is shown over here, we obtain the answer in this form. We have multiplied these terms, this is the numerator part over here, a1 plus iota b1, a2 minus iota b2, it is a2 plus iota b2, a2 minus iota b2. When we multiply these terms, we are getting the answer in this form. In the next step, we are taking the mod over here, we are talking about the mod of, this is the value of z1 z2, z1 by z2. When we take the mod, we are getting the answer in this form. So when we take the LCM, and we separate these terms, the numerator part and the denominator part over here. We are talking about, you can look at these calculations over here, you can try these calculations over here. We are saying from this we can reduce it to this particular form. After that we are separating the numerator and denominator because both the numbers, they are positive. So we are writing that this is equal to mod of z1 over mod of z2. So we are saying that z1 over z2 mod, that is equal to mod of z1 over mod of z2, and again the condition we have is that z2 should not be equal to 0, because we are talking about the inverse of z2, so it means z2 should not be equal to 0. The next result we have is that real part of z1 z2, that is equal to real part of z1 into real part of z2 minus imaginary part of z1 into imaginary part of z2. So to prove this result, we are writing z1 is equal to a1 plus iota b1, z2 is equal to a2 plus iota b2. When we are talking about z1 into z2, the answer we have, it is a1 a2 minus b1 b2 plus iota a1 b2 plus b1 a2. So when we are talking about the real part of z1 z2, this is real part of z1 z2 we are saying, so it is a1 a2. a1 is a real part of z1, a real part of z2 minus imaginary part of z1 into imaginary part of z2. When we are talking about the imaginary part of this number, when we are talking about imaginary part of z1 z2, we are getting it is equal to real part of z1 into imaginary part of z2 plus imaginary part of z1 into real part of z2. So we have just written these terms over here in this form. Next is for a and b, these are real numbers. We are given that a and b are real numbers, and z1 z2, these are the complex numbers. We have to prove this result. We are saying a z1 minus b z2 whole square, mod of this term, and mod of plus mod of b z1 plus a z2 square, that is equal to this value. So to prove this result, we start with this first term over here. It is mod of a z1 minus b z2 square. So it is equal to, when we are talking about this value, so this is equal to az1 minus bz2 into az1 minus bz2 bar. We are using the formula that mod of z square is equal to z into z bar. So this is equal to az1 minus bz2 into a and b are real numbers, so we are writing it is az1 bar minus bz2 bar. So when we multiply these terms, we are obtaining it is a square z1 bar plus b square z2 bar minus ab z1 z2 bar minus ab z2 z1 bar. Similarly, we can rearrange these terms and we can write it in the form a square mod of z1 square plus b square mod of z2 square. Then we take a b common, we are writing it is minus a b common, and we are left with this z1 z2 bar minus z2 z1 bar. Next step, we are saying we are calculating mod of bz1 plus az2 whole square. So again we have written it in the form using this formula, that is mod of z square is z into z bar. We have used this formula over here, and on solving this, on multiplying these terms, we obtain the answer in this form. And when we add both these values, look at these values, it is a b z1 z2 bar, this term we have over here, and the sign over here we have it is plus sign. So both these terms, these are same, so these two terms, these gets cancelled, and on adding these values, look at these terms over here, it is a square z mod of z1 square, this is b square mod of z1 square. So when we take mod of z1 square common, we are left with this a square plus b square. Similarly, for the next term, we will have a square plus b square into mod of z2 square. So if we take a square plus b square common, we get it is mod of z1 square plus mod of z2 square, and this is what we have to prove. Next is, if mod of this number z minus iota 5 over z plus iota 5, it is 1. We have to show that z is a real number. So suppose we are saying z is equal to x plus iota y. Then we have the value of mod of z minus 5 iota over z plus 5 iota, that is equal to 1. This implies us that mod of z minus 5 iota is equal to mod of z plus 5 iota. We have already studied this property, that this mod can be separated for both these terms. Now if we square both these values, we get it is mod of z minus 5 iota square, that is equal to mod of z plus 5 iota square. So this implies us that x plus iota y minus 5 square, that is equal to x plus iota y plus 5 square. In place of z, we have substituted x plus iota y. Now value of this term, this mod, it is, this implies us this is equal to x square plus y minus 5 square, this is equal to x square plus y plus 5 square. So this x square gets cancelled, and this gives us that x y minus 5 square, that is equal to y plus 5 square. And this thing implies us, and we are talking about this value, we get it is y minus 5 is equal to plus minus y plus 5. So we are talking about two cases, y minus 5 is equal to y plus 5, and second is y minus 5 is equal to minus y minus 5. So this case is not possible. We are saying this particular case, this is not possible, because we are getting minus 5 is equal to 5. So we are left with this case. So we are getting 2y is equal to 0. So the value of y we are getting is equal to 0. So we are saying the number we have, it is z is equal to x plus iota y, and we have obtained that the value of y is equal to 0. So the number we have, it is z is equal to, the number we are having, it is z is equal to x, and this is what we have to prove, that the number is purely a real number. We are saying z is a real number. This thing we have proved, that z is equal to x. Next is, if a plus iota b is equal to this value, we have to prove that the value of a square plus b square is equal to this. So if we compare both these values, this is basically we are talking about a plus iota b, and this number we are saying this is basically the mod of a plus iota b square. So we have to calculate the mod of this number. So to calculate the mod, we are going to separate the real and imaginary parts. And to separate the real and imaginary parts, we have x plus iota square divided by 2x square plus 1. So in the numerator we have, it is x square minus 1 plus 2 iota x over 2x square plus 1. So we are writing this is equal to x square minus 1 over 2x square plus 1 plus iota 2x over 2x square plus 1. So if we are going to do the take the mod over here for both this value we are talking about, it is a plus iota b is equal to this. So when we are talking about the mod of a plus iota b square, that is basically equal to, we are saying a square plus b square. So the answer we are getting, it is x square minus 1 over 2x square plus 1 whole square plus 2x by 2x square plus 1 whole square. So it is equal to x raised to the power 2 minus 1 whole square plus 2x square divided by 2x square plus 1 whole square. Now talking about this numerator part, we will get, it is x raised to the power 4 plus 1 minus 2x square plus 4x square. So the answer on solving this, we will obtain the answer for this, we are getting, it is x raised to the power 4 plus 2x square plus 1, and this is equal to x square plus 1 whole square. So we are saying that this numerator part, it is x square plus 1 whole square. The denominator we have, it is equal to this, and this is the result that we have to prove in this case. Next is, if p plus iota q, this value we are talking about, p plus iota q, that is equal to a plus iota square over 2a plus iota, we have to calculate the value of p square plus q square. So again, if we look at this value, this is basically we are talking about the mod of this number p plus iota q square. So we have to separate the real and imaginary parts over here. So the number we have, it is a plus iota square divided by 2a minus iota. So if we open this whole square term, we are getting, it is a square minus 1 plus 2a iota divided by 2a minus iota. Now the next step we have to do is, we have to take the mod of this term. We are talking about the mod of this term. So that will be equal to mod of a square minus 1 plus 2a iota divided by mod of 2a minus iota. So it is equal to a square minus 1 whole square plus 2a square divided by 2a square plus 1. So on solving this, we will obtain, it is equal to a raised to the power 4 plus 1 minus 2a square plus 4a square divided by 4a square plus 1. So this is equal to a square plus 1 whole square divided by 4a square plus 1. This term will become plus 2a square, and this will become the formula for this term, and this is the result that we have to prove when we are taking the mod. And we are missing over here one thing, it is square of this mod. So we are having square of this mod, so these terms are in this way, otherwise we will have the square root over here. So this is the value that we have to calculate. We are saying the value we have to calculate it is p square plus q square, that is equal to the square of this mod. So we obtain this answer. Next is, let z be a complex number such that mod of 1 minus iota z over z minus iota, that is equal to 1. We have to prove that z is purely real. So we can separate the mod function with the numerator and denominator. So we get 1 minus iota z is equal to mod of z minus iota. Now if we square both sides, we obtain 1 minus iota z square, that is equal to mod of z minus iota square. So if we substitute over here that z is equal to x plus iota y, then we will have this is mod of 1 minus iota into x plus iota y square, that is equal to x plus iota y minus iota square. So this will become 1 plus y minus iota x square, that is equal to mod of x plus y minus 1 iota square. So this is 1 plus y square plus x square is equal to x square plus y minus 1 square. So this x square gets cancelled. So we are left with is 1 plus y square plus 2y, that is equal to 1 plus y square minus 2y. Y square gets cancelled, 1 get cancelled, and we are left with is y is equal to 0. So when y is equal to 0, the number we have assumed, it is z is equal to x plus iota y. We are saying y is equal to 0. It means the number we are left over here, it is z is equal to x, and this number is purely a real number because x and y, these are the real numbers. And this is what we have to prove. We have to show that z is purely real. Now in this next question, it is given that z1 and z2, these are two numbers, and they are satisfying that 2z1 over 3z2 is purely imaginary. So it means 2z1 over 3z2, that is equal to iota k for some k which is real, because it is given that it is purely imaginary. So we can write it in this form. Now we have to prove this result, that mod of z1 minus z2 over z1 plus z2 is equal to 1. So we are writing it is mod of z1 minus z2 over z1 plus z2. This is equal to mod of z1 minus z2 divided by mod of z1 plus z2. So if we take common z2 from the numerator, we are getting it is z1 by z2 minus 1 mod divided by mod of z1 by z2 plus 1. So this is equal to, when we are talking about z1 by z2 over here, the value we have it is, if we multiply this equation by 3 and divided by 3, we multiplied by 3 and divided by 3, divided by 2. These values get cancelled. So value of z1 by z2 we have it is 3 by 2 k iota minus 1 divided by 3 by 2 k iota plus 1. Now we are talking about the mod of these numbers. So the modulus of these numbers are, we are looking at these numbers, the modulus of these numbers are 3 by 2 k square plus 1 divided by 3 by 2 k square plus 1, and it is square root of whole of this term. And we can clearly see both these values are equal, so these get cancelled. So answer we are left with is 1, and this is what we have to prove. Next is, if z1 equal to z2 is equal to z3, so on zn is equal to 1. Mod of all these numbers is 1. We have to prove this result. So if we have mod of z1 is equal to mod of z2, so on up to is equal to mod of zn is equal to 1. So this thing implies us that mod of z1 square is equal to mod of z2 square, so on up to is equal to mod of zn square, it is equal to 1. So this implies us that Z1 bar is equal to Z2 bar is equal to Zn bar. This is equal to 1. So this implies us that Z1 bar, that is equal to 1 by Z1, Z2 bar is equal to 1 by Z2, so on up to Zn bar is equal to 1 by Zn. Now we have to calculate the value of this term. Look at this term over here, it is 1 by Z1, 1 by Z2, 1 by Zn. So if we substitute these values over here, we obtain, it is this equation we are talking about. This will become mod of Z1 plus Z2 bar conjugate plus so on up to plus conjugate of Zn. This is equal to, we can write it is Z1 plus Z2 plus so on up to plus Zn whole conjugate, and this is equal to mod of Z1 plus Z2 plus Z3 so on up to plus Zn, and this is what we have to prove. Next is, if a plus iota b over c plus iota d is equal to x plus iota y, we have to prove these two results. So look at this first result. If we compare this value a plus iota b over c plus iota d with this, so clearly we can see that this value is the conjugate over here. So if we are writing a plus iota b over c plus iota d equal to x plus iota y, and we take the conjugate of both these terms, we will obtain a minus iota b over c minus iota d is equal to x minus iota y. This is our first part. And the second part we have, it is a square plus b square over c square plus d square. So basically we are talking about a plus iota b over c plus iota d. If we multiply it with, we are taking the mod and square, it is equal to x plus iota y, we are taking the mod and square. So when we are talking about the mod square over here, so we are writing this term, we can write it in the form a plus iota b into a minus iota b. We can write z mod square is equal to z into z bar over c plus iota d into c minus iota d. It is equal to x plus iota y into x minus iota y. So if we multiply the numerators over here, the answer we will get, it is a square plus b square. We multiply the denominators over here, we are getting it is c square plus d square, and multiplying these terms will give us x square plus y square, and this is the second part that we have to prove. Now in this next question, we are given that if this term is equal to x plus iota y is equal to square root of a plus iota b divided by c plus iota d, we have to prove this result. So clearly we have x square plus y square over here, it means we are talking about the modulus of this number. So we are writing x minus iota y, the conjugate of this number will be c a minus iota b over c minus iota d. Next, if we multiply both these numbers, we obtain, by multiplying both these, we will obtain it is x square plus y square is equal to square root of, by multiplying these numbers, the numerators are multiplied, we get it is a square plus b square, denominators are multiplied, we get it is c square plus d square. So the final answer we obtain, it is x square plus y square whole square, that is equal to a square plus b square divided by c square plus d square. This is the value we are getting over here, and this is what we have to prove. Next is, if 1 plus iota, it is given that 1 plus iota into 1 plus 2 iota into 1 plus 3 iota so on up to 1 plus n iota, this is equal to x plus iota y, we have to prove this result. Now comparing both these values, again this is x plus iota y over here, this time we have x square plus y square, it means we are talking about the modulus of this term. So if we take the mod over here, when we are talking about the mod over here, we have taken the mod over here and we have squared these values. So this left hand side right hand side we get it is x square plus y square. Now coming to this, the right hand side we have it is mod of 1 plus iota square into mod of 1 plus 2 iota square, so on up to mod of 1 plus n iota square. Now when we calculate these mods, the value of this mod it is 1 square plus 1 square, it is square root is not required because it is square over here. Then the next value is 1 square plus 2 square, so on up to the next value is 1 square plus n square. So 1 square plus 1 square means we are talking about the value 2. 2 square plus 1 square means we are talking about the value 5. Then next will be 1 plus 9, that is equal to 10, and so on up to 1 plus n square, and this is equal to x square plus y square, and this is what we have to prove. This is what we have to prove. Next is, this is given to us that a plus iota b into c plus iota d into this term is equal to a plus iota b. We have to prove the result in this form. Again, if we compare both these values, what we get is, it is a plus iota b. We can see that it is a square plus b square. So basically we are talking about the mod of these numbers. So it is mod of a plus iota b square, mod of c plus iota d square, so on up to mod of g plus iota h square. In between these it is e, mod of e plus iota f square, that is equal to a plus iota b mod square. This value we get it is a square plus b square. This value we will have it is a square plus b square, c square plus d square, e square plus f square. This is g square plus h square, and this is what we have to prove. This is the value that we have to prove. Next is, if alpha and beta are different complex numbers such that mod of beta is equal to 1, we have to show this result. So to evaluate this value, we start with this value, it is beta minus alpha over 1 minus alpha bar beta square, and we know that this is equal to beta minus alpha over 1 minus alpha bar beta into beta minus alpha over 1 minus alpha bar beta, and it is conjugate over here. So this thing is equal to beta minus alpha into beta bar minus alpha bar divided by 1 minus alpha bar beta into 1 minus alpha beta bar. So if we multiply these terms, it is beta beta bar minus beta alpha bar minus alpha beta bar plus alpha alpha bar divided by 1 minus alpha beta bar, then minus alpha bar beta, then plus alpha alpha bar beta beta bar. So what is the value of beta bar? It is mod of beta square. This value we have it is plus mod of alpha square, and next we have it is minus of alpha beta bar plus beta alpha bar divided by 1. This value we have it is plus mod of alpha square, mod of beta square minus alpha beta bar plus alpha bar beta. Now it is given in this question, that mod of beta is equal to 1. So this value is equal to 1, this value is equal to 1. So what we obtain is, if we substitute this is equal to 1 and we substitute this is equal to 1, we can see that both the numerator and denominator, they are same now. we are substituting both these values equal to 1, both the numerator and denominator are same, and both are cancelled out, and we are left with the final answer as 1, and this is what we have to prove. This is the value that we have to prove. Next is, if this equation is given to us, it is mod of z square minus 1 is equal to mod of z square plus 1. We have to show that z is imaginary. So we are going to substitute over here z is equal to x plus iota y. So we obtain z square is equal to x square minus y square plus 2 iota xy. Mod of z square is equal to x square plus y square. So if we substitute these values in this equation, we will obtain, we substitute both these values in this equation, we are substituting these values. So we obtain, it is mod of x square minus y square minus 1 plus 2 iota xy, that is equal to x square plus y square plus 1. Now if we square both sides of this equation, the value we have over here, it is x square minus y square minus 1 whole square plus 2xy whole square, that is equal to x square plus y square plus 1 whole square. So to solve this equation, we are going to shift this term on this side, and we obtain, or we are shifting this term, on this side. We obtain, it is 4x square y square, that is equal to x square plus y square plus 1 whole square minus x square minus y square minus 1 whole square. So it is equal to x square plus y square plus 1 plus x square minus y square minus 1 into x square plus y square plus 1 minus x square plus y square plus 1. So when we solve these values, we are writing, it is y square is cancelled, this 1 is cancelled, x square is cancelled. So what we get is that 4x square y square, that is equal to, from these terms we are left with is 2x square, and from these terms we are left with is 2 times y square plus 1. So one value we are getting, this 4 gets cancelled, x square is equal to 0, or y square is equal to y square plus 1. So this does not give any value, I am not having any value of y. So what we get from this is that x is equal to 0. So we have assumed that the number we have, it is z is equal to x plus iota y, and we have obtained that x is equal to 0. It means that the number z is purely imaginary number, and this is what we have to prove. Now next we have is, if this equation is given to be equal to 0, then we have to show that mod of z is equal to 1. So it is being given that iota z cube plus z square minus z plus iota is equal to 0. So if we divide this equation by iota, we obtain, it is z cube plus z square by iota minus z by iota plus 1 is equal to 0. We know that 1 by iota, it is equal to minus iota. We get, it is z cube minus iota z square plus iota z plus 1 is equal to 0. So this is z square into z minus iota plus, look at these two terms, we cannot take anything common right now, but if suppose we are writing in place of this plus 1, we are writing it is minus iota square. Iota square we know it is minus 1, so we are writing it is minus iota square. So from these two terms we can write iota common, and we will be left with z minus iota is equal to 0. So we are getting z square plus iota into z minus iota is equal to 0. This step is important over here. We are saying in place of this 1 we are writing it is minus iota square. So we have taken iota common and we get it is z minus iota. So what we get from this is, from these equations we are getting z is equal to iota, or we are getting z square is equal to minus iota. So in both these cases, if we calculate the value of mod z, the answer we have it is 1. And in this case also, if we calculate the value of mod z square, so that is equal to mod of this, that is equal to 1. This is equal to, this implies us that the value of mod z square is equal to 1. This implies us the value of mod z is equal to 1. So we can see from this that in both these cases, either z is equal to iota or z square is equal to minus iota, what we get is that mod of z is equal to 1, and this is what we have to prove. This result is what we have to prove. Next is find all non-zero complex numbers z which satisfy this equation. So this equation is given to us. It is z bar is equal to iota z square. So if we assume that z is equal to x plus iota y, so what is given to us is that x minus iota y is equal to iota into x square minus y square plus 2 iota x y. So we are writing x minus iota y is equal to iota times x square minus y square minus 2x y. So if we compare the coefficients over here, we get x is equal to minus 2xy, and second we are getting it is y is equal to, or minus y is equal to x square minus y square. These are the two equations we are getting from this. So it is from this equation we can write x common, and we are left with this 1 plus 2y is equal to 0. So we get either x is equal to 0 or we get y is equal to minus 1 by 2. And from the second case, the following cases are arising over here. The first case is when we are considering the value of x is equal to 0. We are saying when x is equal to 0, then this equation gives us minus y is equal to minus y square. So we get the value of y is equal to 0 or 1. So the answers we have is, the numbers we have is z is equal to 0, or the number we have is z is equal to iota. That is x is equal to 0, y is equal to 1, x is equal to 0 and y is equal to 0. The second case we have is when we are considering y is equal to minus 1 by 2. So in this case, when we are considering y is equal to minus 1 by 2, the equations they come in this form, that it is x square minus 1 by 2 square plus minus 1 by 2 is equal to 0. So on solving this, we will obtain the value of x is equal to plus minus root 3 by 2. The value of y we have it is minus 1 by 2. So the answers we are getting over here, it is root 3 by 2 minus iota by 2, or it is not or over here, and minus root 3 by 2 minus iota by 2. So the required complex numbers, the non-zero complex numbers that were being asked, so required non-zero complex numbers, they are iota, root 3 by 2 minus 1 by 2 iota, minus root 3 by 2 minus 1 by 2 iota. So these are the required numbers which satisfy these conditions. Next is we have to solve the equation z square is equal to z conjugate. So again, if we substitute z is equal to x plus iota y, we are substituting this value, then this equation we are saying this will come in the form, it is x plus iota y square, that is equal to x minus iota y. So if we open this whole square, we get it is x square minus y square plus 2 iota xy is equal to x minus iota y. Now if we compare the real and imaginary parts, we will have x square minus y square is equal to x, and x into y, 2x into y is equal to minus y. So if we look at this equation over here, we obtain it is 2x plus 1 into y is equal to 0. So we obtain the values over here. One value we obtain it is y is equal to 0, and second we obtain is x is equal to minus 1 by 2. Now to solve this first equation, using this first equation, we are saying we are having two cases. If we substitute y is equal to 0 in this, we will obtain x square is equal to x, and if we substitute x is equal to minus 1 by 2 in this, we will get it is 1 by 4 minus y square is equal to minus 1 by 2. So this equation gives us x is equal to 0 or x is equal to 1, and this equation gives us 1 by 2 plus 1 by 4 is equal to y square. So we obtain the value of y square is equal to 3 by 4. So this implies us y is equal to plus minus 3 by 4. So the final answers we obtain, we are saying the numbers we have assumed it is x plus iota y. So when y is equal to 0, we are having x is equal to 0 and 1. So one number we have it is 0 when we are taking x is equal to 0 and y is equal to 0, and second number we have it is 1 plus it is basically iota 0. And from this the answers we are obtaining, y value, x value we have it is minus 1 by 2, and the value we have it is plus 3 by it is square root of this term. So plus minus square root of this term, so it is square root of 3 by 2 iota, and it is minus square root of 3 by 2 iota. So these are the answer, these are the values of z that we can have. These are the values we are talking about. Next is for all complex numbers z1 and z2, we have to prove this result, that mod of z1 plus z2 square plus mod of z1 minus z2 square, this is equal to 2 times mod of z1 square plus z2 mod of z2 square. So when we are trying to solve this, we look at this value over here, we are talking about this first value. We are saying we can write this is equal to z1 plus z2 into z1 plus z2 conjugate. So this is equal to z1 plus z2 into z1 conjugate plus z2 conjugate. We are having this value. So if we multiply these terms, we will obtain it is z1 conjugate plus z2 conjugate plus z2 conjugate plus z1 conjugate. So this value is equivalent to mod of z1 square plus mod of z2 square, and it is plus z2 bar plus z2 z1 bar. Next we are talking about this value, so we get it is mod of z1 square plus mod of z2 square minus, when we will multiply these terms it will be negative sign over here. So when we multiply these values, these two values will be negative, so it is z1 z2 bar minus z2 z1 bar. Now if we add both these values, these terms will be cancelled, and we are left with is 2 times mod of z1 square plus mod of z2 square. We are left with this value, and this is what we have to prove. Now next it is given that if we divide fz by z minus iota, the remainder we obtain it is iota. So when we are dividing it by z minus iota, means we are talking about it is basically z is equal to iota. We are talking about it is z is equal to iota. If we equate this term equal to 0, we get z is equal to iota. So it means f of iota, when we are talking about, its answer is iota. Second thing we have is dividing it by z plus iota, we are equating it to 0. It means z is equal to minus iota. So we have f of minus iota is equal to 1 plus iota. This value is 1 plus iota. Now next what we have to calculate over here is, we are saying find the remainder by the division of fz. If we divide fz by z square plus 1. So we are talking about over here, we are saying that when this fz is divided by z square plus 1, we have to calculate the remainder, and as the degree over here, this term, it is z square. So the whatever the remainder we will have, it will have degree at most 1. So it will be of the form az plus b. And suppose the quotient we have over here, it is say gz. We are saying when we divide fz by z square plus 1, the remainder we have, it is of the form az plus b, and the quotient we have, it is g times z. So it means we can write this fz is equal to z square plus 1 into gz plus az plus b. Now we have two values. First is f of iota is equal to iota. So if we substitute iota over here, we get f of iota is equal to iota square plus 1 into g of iota plus a into iota plus b, and this value is equal to iota. So iota we square, we know it is minus 1, so this whole term will become 0, this term gets cancelled. So what we are left over here is that iota a plus b is equal to iota. So this is one equation that we are getting over here. Second equation we will get by substituting this value. We are saying f of minus iota is 1 plus iota, that is equal to f of minus iota. So that is minus iota square plus 1 into g of minus iota plus a into minus iota plus b. Again, if we look at this value, minus iota square, this whole term will become 0. So we will have minus iota a plus b, that is equal to 1 plus iota. So if we solve these two equations, we are talking about these two equations. One is b plus iota a is equal to iota, and second we are saying is that b minus iota is equal to 1 plus iota. So if we add both these equations, we will get 2b is equal to 1 plus 2 iota. So this implies us that b is equal to 1 by 2 plus iota. And if we substitute this value of b over here, we will obtain the value of a is equal to 1 by iota into iota minus b. So this is equal to 1 by iota into iota minus b, means we are talking about it is 1 by 2. So this is equal to 1 by 2 iota. So we are having over here the answer as b is equal to 1 by 2 plus iota and a is equal to iota by 2. These are the two values that are required over here. Next is, if x minus 3 over 3 plus iota plus y minus 3 over 3 minus iota, that is equal to iota, then we have to calculate the value of x and y. X and y, these are real. So to solve this, we are going to cross multiply these terms over here. So we will get it is x minus 3 into 3 minus iota plus y minus 3 into 3 plus iota. This is equal to iota into 3 plus iota into 3 minus iota. So on solving this term, it is iota into 3 square plus 1. So that is equal to 10 iota. And if we multiply the terms over here, these terms when we multiply, we get it is 3x minus iota x minus 9 plus 3 iota. Then it is 3y plus iota y, it is minus 9 and it is minus 3 iota, that is equal to 10 iota. So this 3 iota gets cancelled. So we have the values over here in this form, and if we compare, if we write them in the form 3x plus 3y minus 18, this is the real part, and the imaginary part we have taking, it is plus iota common, so it is y minus x is equal to 10 iota. So what we get is that 3x plus 3y minus 18 is equal to 0. It means x plus y minus 6 is equal to 0. And second equation we are getting from this is y minus x is equal to 10. So if we write them in the standard form we are talking about, it is x plus y is equal to 6 and minus x plus y is equal to 10. If we add these two equations, we will get 2y is equal to 16. So this implies us y is equal to 8. If we substitute this value over here, we will get x is equal to minus 2. So these are the required values over here, that x is equal to minus 2 and y is equal to 8. So we get the values of x and y. Now the next question we have is that a plus iota b raised to the power 5, it is given to be p plus iota q, and we have to prove that b plus iota a raised to the power 5 is equal to p plus iota q plus iota p. So we are talking about this term, it is a plus iota b raised to the power 5, this is equal to p plus iota q. So if we take the conjugate of this whole term, we are talking about the conjugate of this whole term, so this implies us that a minus iota b raised to the power 5, that is equal to p minus iota q. So this thing implies us, if we write minus iota common, we are left with is minus a by iota plus b raised to the power 5, this whole term raised to the power 5, this power 5 we have over here, that is equal to p minus iota q. So this implies us that minus iota raised to the power 5 into, what is 1 by iota? It is minus iota, so it is a iota plus b raised to the power 5 is equal to p minus iota q. Now look at this value over here, what is minus iota raised to the power 5? We are writing it is minus sign is there, so it is iota raised to the power 5, this is equal to minus sign is there, iota raised to the power 4 into iota raised to the power 4 is 1, so we are left with is minus iota. So this implies us that a iota plus b raised to the power 5, that is equal to, we are multiplying this term over here, we are getting it is minus 1 by iota into p minus iota q. So this is equal to iota into p minus iota q. So this is equal to p iota plus q, because again iota square, that will be equal to plus 1. So this minus sign will become plus. So what answer we are getting over here is that b plus iota a raised to the power 5, we are talking about this term, that is equal to q plus iota p, and this is what we have to prove. This is what we have to prove. Next is find real theta such that this term is given to us, it is 3 plus 2 iota sine theta divided by 1 minus 2 iota sine theta. First thing that is given, it is purely real, and second that is given, it is purely imaginary. So we have to write this in the form of a plus iota b. Basically we have to do this thing. So we are talking about the term 3 plus 2 iota sine theta divided by 1 minus 2 iota sine theta. So if we multiply and divide this term by 1 plus 2 iota sine theta and divide it by 1 plus 2 iota sine theta, the numerator part we will get when we multiply these terms, it will become 3 plus 6 iota sine theta, then it is plus 2 iota sine theta, and then it is minus 4 sine square theta, and it is divided by 1 plus 4 sine square theta. So separating the real and imaginary parts, we obtain it is these two terms. Yes, it is 3 minus 4 sine square theta over 1 plus 4 sine square theta plus iota 6 sine theta plus 2 sine theta divided by 1 plus 4 sine square theta. Now we are talking about two cases. One is when this number is purely real, and second when this number is purely imaginary. So when this number is purely real, it means this term is equal to 0. So we get 6 sine theta plus 2 sine theta, it is total 8 sine theta. This value should be equal to 0. So this implies that sine theta is equal to 0. So this implies that theta is equal to n pi. So we are saying when theta is equal to n pi, this number is purely a real number. And the second case we are talking over here, it is when it is purely imaginary, we are saying this term should be 0. So we get 3 minus 4 sine square theta is equal to 0. So we get sine square theta is equal to 3 by 4. So we can write this as sine theta is equal to square root of this term, it is root 3 by 2. So that should be equal to sine pi by 3. The value we should have over here, it is plus minus sine over here. So we are writing it is we have sine pi by 3 over here. We will have plus minus sine over here. So we are getting the answer. We know how to solve these kind of equations. The answer we are getting, it is theta is equal to n pi plus minus pi by 3. So for this value, the number will be purely imaginary, and for theta is equal to n pi, this number will be purely a real number. Next is find real values of x and y for which the complex numbers, this and this, these are the two complex number given, and they are conjugate to each other. So if we consider that this first number is conjugate of other, so we are talking about 3 plus iota x square y conjugate, that is equal to x square plus y plus 4 iota. So we are getting it is minus 3 minus iota x square y, that is equal to x square plus y plus 4 iota. So on solving this, we will obtain, this is the real part we have, it is x square plus y is equal to minus 3, and the imaginary part we are having over here, it is minus x square y is equal to 4. So from this second equation, we are talking about this second equation over here, this thing implies us that x square, that is equal to minus 4 by y. So when we substitute this value over here, we get it is minus 4 by y plus y is equal to minus 3. So this implies us minus 4 plus y square is equal to minus 3y. So this implies us y square plus 3y minus 4 is equal to 0. And on solving this quadratic equation, we get it is y square plus 4y minus 4 is equal to 0. So this implies us y into y plus 4 minus y plus 4 is equal to 0. So we get y is equal to 1 and minus 4. Now by substituting this value y is equal to 1 and minus 4 in these equations, in this equation we are talking about, we are substituting this value in the equation, x square is equal to minus 4 by y. When we substitute y is equal to 1, this implies us x square is equal to minus 4, and when we substitute y is equal to minus 4, we get x square is equal to 1. Now it is given that x and y, these are real numbers. We are being given over here that x and y, these are the real numbers. It means x square cannot be equal to minus 4. This thing is not possible for x being a real number. So what we get is that is the possible values of x, they are plus, minus and 1, because x square is equal to 1. So this thing implies us x is equal to plus minus 1. So the final answer we obtain over here, it is x is equal to plus minus 1 and y is equal to minus 4, because this is the value corresponding to y is equal to minus 4. Corresponding to the value we are talking about over here, y is equal to 1, we are not having any value of x. So this is our final answer, that x is equal to plus minus 1 and y is equal to minus 4. Next is, if x is equal to minus 5 plus 2 root minus 4, it means it is given that x is equal to minus 5 plus this value will become this root minus 4, this will be 2 iota, so it is 4 iota. We are talking about x is equal to minus 5 plus 4 iota. We have to calculate the value of this term. So we can write it is x plus 5 is equal to 4 iota. If we square this term, we get it is x square plus 10x plus 25 is equal to minus 16. Now we have to write this term in this form. So to write this term over here, first of all we are simplifying this term. We are having it is x square plus 10x plus 41 is equal to 0. So if we divide both these values, we are talking about x raised to power 4 plus 9x cube plus 35x square minus x plus 4, and if we divide this value with x square plus 10x plus 41, we will obtain the quotient is x square minus x plus 4, and the remainder we will get, that will be 160. So you can check this calculation, that you will get the quotient as this value and remainder is minus 160. So what this thing gives us, that we can write this term, we are talking about this term, we can write this term as this value, where when we are looking at this value over here, or we are talking about this value, this whole term is present over here and its value is equal to 0. So we are saying that the value of this term, that will be minus 160, and this is what we have to evaluate. Next is, let z be a complex number satisfying this equation. This quadratic equation is given to us in z. It is z square minus 3 plus iota z plus lambda plus 2 iota is equal to 0. Then it is given that if we suppose that this equation we are talking about, it has a real root. It has one real root. A real root means it has one real root. Then we have to find the non-real root. So if it is given that this equation has a real root, so suppose we are saying that alpha is the real root. Alpha is the real root. So in that case, for this real alpha, alpha belongs to R, we are having alpha square minus 3 plus iota into alpha plus lambda plus 2 iota is equal to 0. So we can write this as alpha square, we are separating the real and imaginary parts, minus 3 alpha plus lambda plus iota into 2 minus alpha is equal to 0. So on comparing the real and imaginary parts, we are writing it is alpha square minus 3 alpha plus lambda is equal to 0. And on comparing this imaginary part to 0, we are getting 2 minus alpha is equal to 0. So this implies us alpha is equal to 2. So what we get is that alpha is equal to 2 is a real root of this equation. So let beta be the complex root, or we are saying it is the non-real root. So clearly this equation is a quadratic equation in Z, and if alpha and beta are its roots, then the value of alpha plus beta, that will be equal to 3 plus iota, that is minus b by a. The value of alpha we have calculated, it is equal to 2. So we are getting 2 plus beta is equal to 3 plus iota. So this implies us beta is equal to 1 plus iota. So this is the root that we have to calculate. We are saying let beta be the non-real root. We have obtained the value of beta is equal to 1 plus iota. So the non-real root we have it is 1 plus iota, and the real root we are saying it will be alpha is equal to 2. Now the next question we have is to find the greatest and the least values of mod z when some condition is given to us. So the first question that we have over here, it is this condition is given that mod z minus 2 plus iota is less than equal to 2. We have to find the greatest and the least values of mod z. So if we look at this equation, we have z minus 2 plus iota mod. We know that this is greater than equal to mod of z minus mod of 2 minus iota. This formula we have already studied. Now what is the value of mod of 2 minus iota? We are getting it is z minus 2 plus iota. This is greater than equal to mod of z minus, this value will be 2 square plus 1 square root. So that will be equal to square root of 5. This value we will have it is equal to square root of 5. So we have this equation, we have this equation, we are having two equations now. So from these two equations we can write mod of z minus root 5 is less than equal to mod of z minus 2 plus iota is less than equal to 2. Now what we want to obtain is we want to find the least and the greatest value of mod z. So we are considering this part and this part of the equation. So what we get is that mod of z minus root 5 is less than equal to 2. So this thing implies us minus 2 is less than equal to mod of z minus root 5 is less than equal to 2. So this thing implies us that root 5 minus 2 is less than equal to mod z is less than equal to root 5 plus 2. So this is the required value. We are saying that the minimum value that mod z can have it is root 5 plus 2. This is the root 5 plus 2, this is the maximum value, and root 5 minus 2, this is the least value of mod z. Next is, if z is any complex number which satisfies mod of z plus 4 is less than equal to 3, we have to calculate the greatest value of z plus mod of z plus 1. So the value that is given to us is mod of z plus 1 we want to calculate. We are writing this is equal to mod of z plus 4 minus 3. Why we are writing it in this form? Because the value we require, well, this z minus 4, for z minus 4 we have this inequality. So from this equation we can write this is less than equal to mod of z plus 4 plus mod of minus 3, and mod of z plus 4 is given to be less than equal to 3. So we are writing it is less than equal to 3 plus 3 is equal to 6. So what we obtain is that mod of z plus 1 is less than equal to 6. It means the greatest value of this mod of z plus 1, it can be 6. It cannot be greater than 6. Next is, if mod of z1 is equal to 1, it is given that mod of z1 is equal to 1, mod of z2 is equal to 2, mod of z3 is equal to 3, and mod of this term is equal to, this whole term we are talking about, it is equal to 6. We have to calculate the value of mod of z1 plus z2 plus z3. So now look at these terms over here. We are saying if mod of z1 is equal to 1, it means z1 bar, that is equal to 1. We are talking about this value. We want to calculate the value of this term. We are saying mod of z1 is equal to 1. It means mod of z1 square is equal to 1. So this thing implies that z1 bar is equal to 1. So this means that z1 bar, that is equal to 1 by z1. Similarly, for the second term we will have z2 bar, that is equal to 4 when we will do the square over here. So this thing implies us that z2 bar is equal to 4 by z2, and in the third case we will obtain z3 bar is equal to 9 by z3. Next, the value of this term is given to be equal to 6. So if we substitute these values over here, in terms of, we require the answers in terms of z1, z2 and z3. So we are writing it is mod of 9z1 z2 plus 4z3 z1 plus z2 z3. This is equal to 6. Now if we multiply and divide this equation by, we are multiplying this equation by z1, z2, z3 mod. We are dividing it by z1, z2, z3. It is mod already over there. This is divided by z1, z2, z3 divided by z1, z2, z3. So what we get is that mod of z1, z2, z3 into mod of, now look at this term over here, this will become 9 into 1 by z3 plus 4 into 1 by z2 plus 1 by z1 is equal to 6. So we get mod of z1, z2, z3 into, we are talking about 9 by z3, this is z3 bar plus z2 bar plus z1 bar, this is equal to 6. We are talking about this value over here. We have substituted these values in these equations, 1 by z3, 1 by z2 and 1 by z1, and we obtain the answer in this form. And we know that the value of this, it is mod of z1, mod of z2, mod of z3, and this value when we are talking about, it is equal to mod of z1 plus mod of z2 plus z3, and this value is given to be 6. Now these individual mods, the value of these three individual mods, it is given to us. So we are writing that 1 into 2 into 3 into mod of z1 plus z2 plus z3, that is equal to 6. So this implies us that mod of z1 plus z2 plus z3 is equal to 1. So this is the required value. This is the required value. We have to calculate the value of mod of z1, z2, z3. So we can see that the value of this term, it is equal to 1.